PSV means process safety valve, or you can say pressure safety valve also. Now, one thing we regularly use in our kitchen, that's a pressure cooker, right? It's a very common utensil, and we need a pressure cooker to cook the food very fast, right? If you want to boil some food in water, then in normal condition, in an open vessel, the water will boil normally at 100 degrees centigrade, and the temperature will not go up. Okay, temperature will be fixed at 100 degrees centigrade. So the food may take quite some time to get cooked. But if you pressurize it inside a pressure cooker, then the boiling point of the water becomes quite high. As a result, the food gets cooked very fast. So that's the principle behind the pressure cooker. Now you might have seen in the pressure cooker, if this is the pressure cooker, then on the lid, you will find a weight over there, right? So that is the pressure safety valve. Okay. Now when the pressure inside the pressure cooker, it is very high, then the weight goes up and the steam gets released and the pressure goes down. Okay. So then that weight again sits on the lid, right? So this is the pressure safety valve, which are very commonly seen. And it also has a rupture disc. You might have seen on the lid somewhere, you will find a very small disc of this nature. Okay, they are tightly placed on the lid. So that is called rupture disc. I mean, sometimes if the pressure safety valve fails to open, then the rupture disc is an additional layer of safety. The rupture disc gets ruptured or burst so that the remainder of the pressure vessel, or the pressure cooker rather, that is safe. Okay, so that's how the pressure cooker operates, and we all know how it is done. So this PSV and rupture disc, these are very common. And storage tank or low pressure storage tank, it is mostly industrially you will see. I cannot give any household example for that. Now we will learn all of them one by one. So let us understand what a process safety valve or pressure safety valve is. It's a type of pressure relief valve that is designed to protect the equipment, pipelines, and pressure vessels from excessive pressure buildup. Okay, it ensures the safe operation of industrial processes by automatically releasing excess pressure when it exceeds the predetermined limit. Okay, so this is being done through the process safety valve. Now, household application already I have discussed, but there are certain industrial applications as well. For instance, in the oil and gas industry, there are a lot of inflammable gas and other substances are there. So there is a high risk of explosion in the pipeline and the vessel. So in that kind of situation, the use of process safety valve is very necessary. Similarly, in the chemical plant, to protect the reactor and storage tank. So chemical reactor or some chemical storage tanks, they also may undergo certain pressure surge. And in that situation, pressure safety valve is very necessary. In the power plant, we use boiler because through boiler we get steam, which eventually operates the turbine which generates the power. So safety of boiler is very, very important. So we use pressure safety valve in the boiler. And the pharmaceutical and food processing industry, where controlling the pressure and temperature is very, very important in order to maintain the quality of the food or the pharmaceutical products that we are getting. So these are the common application of process safety valve. Now these are the characteristics of a process safety valve. It has automatic pressure relief characteristics, that it opens when the system pressure exceeds the set limit. It is called set pressure. So at set pressure, it opens up and closes once the normal conditions are restored. When the extra amount of pressure is released, then it restores. So the set pressure, it is calibrated to open at a specific pressure to prevent the over pressurization. So that is called the set pressure or design pressure. And the blowdown, that is resetting pressure difference. That means the difference between the pressure at which the valve opens and the pressure at which it resets. That means set pressure is the point where the valve opens. But the pressure cannot go beyond a certain point because we have already opened the valve. So pressure rises up to a certain point and then it gets reduced and the valve sits down as it was in the normal condition. So that is the pressure difference. We call it blowdown or the resetting pressure difference. Then the PSV has very fast response because it is designed to respond quickly to prevent any catastrophic failure, because that is the reason we are using pressure safety valve. It is not a normal control valve. Pressure safety valve needs to be almost like a on-off valve so that its response time is very fast. Then the compatibility with the existing condition should be taken care of when manufacturing the valve, because it needs to be corrosion resistant, because it handles many kind of fluids. There may be corrosive gas, there may be steam, there may be high temperature gas or high temperature liquid. Okay. So the condition of pressure safety valve should not be compromised. It needs to be in a perfect condition so that whenever the situation arises, it acts and the overpressurization is avoided. Okay. Then the capacity rating, that is designed to discharge a specific volume of fluid or gas to ensure pressure reduction. You might have noticed that when you operate a pressure cooker in the kitchen, when the pressure cooker is over pressurized, then the weight gets up for a second or two and certain amount of steam is released and then it sits back. Again, after some time, it opens up and certain amount of steam is released and it sits down. If you could measure the amount of steam released during those two events, you will find that discharged amount of steam is almost same. So although it is not designed so perfectly in pressure cooker, but in industrial cases, the discharge of that specific volume of fluid is properly designed and it releases only that amount of liquid to depressurize the stream. Okay. Then there are various types of PSV, like it can include spring-loaded or pilot-operated or balanced bellows valve, depending upon the application. And there are various compliance with standard that it must adhere to. The industry safety codes like API 520, ASME Section 8, ISO 4126, etc. So these are the characteristics of PSV. Now we will learn a few definitions. First, operating pressure. The operating pressure is the normal working pressure of the system under the steady state condition. So in the example that we have seen, suppose we are talking about this compressor. Okay. So what is the normal working pressure of this compressor? We find it is 69 bar, right? So operating pressure is 69 bar. So the set pressure or design pressure is the pressure where the PSV starts to open. Obviously, it should not be 69 bar because 69 bar is the operating pressure. It can be slightly higher. It may be 75 bar or 80 bar, whatever it is, because you have to give certain gap between the operating pressure and set pressure. Otherwise, it will be unnecessarily activated, So you do not want the PSV to get activated unnecessarily. The relieving pressure is the actual pressure when the valve is fully open and venting fluid. Okay, so relieving pressure is the set pressure plus the accumulation, or it is called the back pressure more commonly. The back pressure is usually 10% of the set pressure as per ASME 8 standard, and it is 21% for fire emergency. Only for fire emergency it is 21%. For all other cases it is 10%. And obviously the operating value is always lower than the set pressure to ensure safe operation. Now we take an example. A steam pipeline may operate at 90 bar, but the set pressure may be 100 bar. So there is a clearance of 10 bar over there. So between 90 to 100 bar, nothing happens. As soon as 100 bar is reached, the safety valve opens. The back pressure is 10% of the 100 bar, hence the relieving pressure is 110 bar. That means set pressure is 100 bar, but the pressure can go up to 110 bar. Okay, so when the pressure gets reduced, it can come down and sit back to 90 bar. So the back pressure in this case is 10 bar only. Okay, so please do not confuse between this 10 bar and this 10 bar. This 10 bar is the clearance. The operating pressure is 90 and set pressure is 100. So between 90 to 100 nothing will happen, but at 100 bar the PSV starts releasing the stream. Okay, and this extra 10% of 100 bar, that is the back pressure. Okay, and from the steam table at 100 bar we may find the temperature to be 317 degrees centigrade because we are talking about steam over here. Okay, so that's how the things work. Now we will understand it better when we take the example that we have opened. So let us go to the example. Okay, now if you want to set the PSV, okay, first let us check where we can place it. Now the highest point of the pressure is over here, 69 bar. It is the gas product and it is liquid product. Both of them are at 69 bar. Okay, this is the maximum condition. So we want to safeguard the compressor with the process safety valve. Okay, now let us add a process safety valve over here. If you hover around this line, you will find a very small rectangular box that is appearing over here. So you have to connect over there. The moment you place, the PSV is attached to the gas product line. Okay, so this is the PSV1. So this is the PSV1. Let us see what are there. Now the operating temperature is 128 degrees centigrade, right? Now we can set a design temperature higher than that. Okay, set temperature maybe say 200 degrees centigrade. And the design pressure, it should be higher than 67.93. Let us say it is 75 bar. Okay, so we have given extra 7.07 bar of clearance. So between 67.93 bar to 75 bar, nothing happens. 74.99 bar, nothing happens. The moment it touches 75 bar, the pressure safety valve should open. Okay. Now go to the scenario. Now there can be multiple scenarios for which you may wish to design your pressure safety valve. What are those scenarios? First, we have to create a scenario. So you create a scenario and then we'll see what it can be. Now first we have to open this scenario. Okay. Let us open the scenario and see what things we have to specify over here. So this is the scenario setup. Now scenario type. These are various possible scenarios for which you may want to design your pressure safety valve. Fire, control valve failure, exchanger tube rupture, distillation column reflux failure, abnormal heat and vapor input, coolant failure, local power failure, and many other things. Okay, you can take one scenario or more than one scenarios for a particular process safety valve to operate. Okay, so let us take this one, abnormal flow through valve. Let us take this particular scenario for an example. So abnormal flow through valve, we can name it accordingly. We can say abnormal flow through valve. Okay. Now you have to choose the reference stream. Okay. Which stream you are working with? Now you are working with this gas product stream. So you have to choose one. So select gas prod. This is the reference stream of yours. Right? Now what is the relieving temperature and relieving pressure? Relieving temperature, you know, this is 82.50. Total back pressure is 7.5. You remember? Back pressure is usually 10% of the set pressure as per ASME 8. So 10% of the set pressure, we had set the pressure to be 75, right? Our set pressure or design pressure is 75. So they have taken in the scenario total back pressure 10% of that 7.5. So 7.5 plus 75, this is the relieving pressure. Right? This is the relieving pressure. Now, relieving temperature. Relieving temperature, you can say 250 degrees centigrade or so. Now, one thing that you will find over here, that is a yellow stripe, which will contain the instruction and any failure notice. Okay, so your target is to make this stripe to be green. The moment you find a green stripe, your process safety valve is properly designed. Okay. Now, it says the relieving flow must be specified. You can manually select a value as per your requirement or choice. Or you can say reference. Reference means you have chosen the reference to be gas prod. So it will take the reference flow of the gas prod. So what is the gas prod flow rate? Gas prod is 4952 kg per hour. So the moment you choose the reference, it will come 4952. And here you see orifice calculation completed, green stripe. Okay. Now here they have done the calculation using direct integration method. Now there are various methods like that. Interested readers can go through each and every type of calculation, but the direct integration or homogeneous equilibrium method is most popular, so it has been chosen over here by default. So this is the homogeneous equilibrium method. It calculates the required flow capacity of PSV when handling two-phase flow, that is the mixture of liquid and vapor, and ensures that the relief system is properly sized to prevent overpressure condition in the vessel or pipeline. The homogeneous mixture properties, that is the two-phase mixture, is treated as single fluid with average property. That means rather than analyzing the liquid and vapor separately, the density is taken as volume average density of two phases. So as if this is a single phase and the density is calculated as volume average density of two phases. Then thermal and mechanical equilibrium, that is the liquid and vapor phases have the same temperature at every point of the flow path, and both phases experience the same pressure throughout the expansion process. So that is the thermal and mechanical equilibrium. And the isentropic expansion, that is the fluid undergoes adiabatic and reversible expansion as it flows through the PSV. Okay, so these are the homogeneous equilibrium method of calculation. This is the homogeneous density calculation. Average density is 1 by x by rho v plus 1 minus x by rho l, where x is the vapor fraction and rho v, rho l are the densities of vapor and liquid respectively. So that way rho HEM is calculated. The mass flux is calculated as 2 rho HEM multiplied by the difference between the enthalpies of inlet and outlet, and the PSV orifice area is calculated as W by G, where W is the mass flow rate. So that way the area is calculated. Now here we find the selection of orifice size, how the orifice is selected. We have to check the required flow of the stream and rated flow, that is the maximum capacity. Rated flow means the maximum capacity and required flow means the actual flow of that stream. In this case it is gas product, which is 4952, as I remember that, 4952 per kg per hour. So that is the required flow rate, and rated flow rate is the maximum capacity. Okay, so orifice size should be such that the percentage used should be 30% to 90%. That means the orifice size should not be so small that over 90% of the usage of the orifice area, or it should not be so large that less than 30% of the orifice is used for the safety valve purpose. Detailed calculation is not within the scope of Aspen Plus. In Aspen Plus, you have to try out with various orifice size, and you will see the percentage orifice area somewhere. I will show you, and from there you have to choose one. Now let us do that. Here we have the sizing. Okay. Now the orifice size, if you choose 0.709, it says the selected orifice is smaller than the calculated orifice. Let us choose a little higher, 1.264. Yeah, this is okay. We are seeing the green stripe. If you still go higher, let us see. 1.980 is also okay. But the moment we choose 3.245, it is quite huge because the relieving capacity is less than 30%. So it should be between 30 to 90, right? Now we will check with this one. Let us go to the fluid properties. These are the relieving and exit conditions of the vapor and orifice sizing. Okay. And this is relief composition. As that particular vapor is getting released through the process safety valve, we may not be able to release it in the atmosphere. You can see 13.33% and 27.45% methane and ethane respectively. So they are very inflammable, right? So we cannot just send it to the atmosphere. We may have to use some flare for that. So that we will see. So for the time being, let us go back to the PSV1. We have checked the scenarios. Now, the inlet and outlet pressure drops are yet to be calculated. And you can see the capacity used is 68.08%. Okay, so it is between 30 to 90. Go to PRD data. Here, what is the type of PRD? Now, is it a relief valve or a rupture disc? Rupture disc we have not studied till now, but if you choose the rupture disc, it will have something else. We'll see. Now it is relief valve, okay? And the design code is ASME 8. You can use something else also. And discharge to flare. Now, what is our pressure? Pressure is almost 69 bar. So, we have to choose high pressure flare. Okay? So that the chance of hazard is reduced. And the relief valve type, it can be conventional, balanced bellow, pilot operated, right? We just learned it. The type of valve, spring loaded, pilot operated, balanced bellow, right? So these are the type of relief valve. Now each and everything has their own sets of pros and cons. So you can go through them from literature. Body material, you can choose from various options. Then go to the rating. Now in the rating, you see the set pressure is 75, allowable overpressure is 10%. Now you can change it. If you want, you can change it also. So percentage of back pressure limit may be altered in the rating tab. If you want, you can make it 11%, 12%, or less than 10% also allowable overpressure as per your requirement. But 10% is very standard. So 75 plus 10% of 75, that is 7.5. So 75 plus 7.5 becomes 82.5, which is relieving pressure. Okay. And this is the selected orifice, which is using 68% of the orifice area. Right. Now, if you choose lower than that, it becomes 100%. So it is not advisable. And if it is 3.245, it is using less than 30%. It is not advisable. If you choose 1.980, it is using 43.46%. Although it is Okay, but why to use a higher one if the lower one is good enough? So this is the percentage orifice area. So line sizing should be such that the calculated pressure drop should be less than maximum permitted limit, that is 3% of the set pressure for inlet and 10% for the set pressure in outlet. So in the inlet condition, it should be less than 3%. In the outlet condition, it should be 10% of the set pressure. Now let us understand the inlet line sizing. That means from the equipment to PSV, this inlet line. How to do the sizing? The objective of the inlet line sizing is to minimize the pressure drop to avoid PSV malfunction. The velocity is calculated by this, where W is the mass flow rate, A is the cross-sectional area of the pipe, and rho is the fluid density. Then the pressure drop is calculated as this one, very well-known equation, where F is the friction factor, Darcy-Weisbach equation. L is the pipe length, D is the pipe diameter, and rho v square, you all know what they are. So that's how the delta P, that is the pressure drop across the inlet line, is calculated this way. And the outlet line sizing, that is from PSV to relief system or atmosphere, wherever you are sending. Relief system means if you are sending it to the flare, so PSV to the flare, that lining. The objective is to ensure the pipe is large enough to avoid excessive back pressure, and the velocity should be below Mach number 0.7, because here Mach number is very important. It is going to the flare, so it should not douse the flare. So Mach number is calculated as V by C, where C is the speed of sound in that medium. If M is greater than 0.7, then you have to increase the pipe size to reduce it down. And if you have to check the back pressure, it is P exit. The exit pressure is calculated as W is equal to CA P exit root over ZT by MW. MW is the molecular weight, Z is the compressibility factor, C is the discharge coefficient, A is the area, T is the temperature, W is the mass flow rate. Okay, and this back pressure should be less than 10%, and if it is more than 10% of the set pressure, then increase the diameter or reduce the length. So that way you can do the line sizing. Now, such detailed calculation, again, it is not within the scope of the person who uses Aspen Plus software. They are done by Aspen Plus software itself. You have to just go and feed the data. Basically, you have to try out various options. Now, what you need to do, you need to choose the lines. So, suppose you choose the line standard, say 40 schedule 40. You know what is schedule 40. Each and every commercial pipelines, they have the identity with the schedule numbers. And let us choose the nominal diameter to be 1 or say 2 and 3. Okay. So nominal diameter 2, that means internal diameter is 2.067. In this case, internal diameter is 3.068. The specified equivalent length has been given, the elevation has been given. Flow rate, let us not check with the rated area, that is the maximum. Let us do it the reference, the required is 4952, right? So we choose 4952 only and run the line sizing. Okay, so it is done. Inlet line pressure drop is checked. Outlet line pressure drop is checked. Okay, so we have got the pressure drop within the limit. So what is the maximum limit? Maximum limit is 2.25 because this one should be 3% of 75, whereas this one is 10% of 75. Okay, so 3% of 75 bar is 2.25 bar, that is for inlet line, and 10% of 75 bar, that is 7.5 bar, that is for outlet line. So this is the maximum one, and calculated dP is less than the maximum one, so everything is okay, right? So our work with the process safety valve is complete.